Good evening, sir. My name is Rihanna. I'm from CSE third year. My topic is asymptotic analysis of complexity bounds index. So, first of all, asymptotic notation is a way to describe the running time or space complexity of an algorithm based on the input size. It is commonly used in complexity analysis to describe how an algorithm performs as the size of the input grows. The three most commonly used notations are big O, omega, and theta. The first one, omega notation. Omega notation represents the lower bound of the running time of an algorithm. Thus, it provides the best case complexity of an algorithm. The execution time serves as a lower bound on the algorithm's time complexity. It is defined as the condition that allows an algorithm to complete statement execution in the shortest amount of time. Here in the right side, the diagram is shown, and let us consider g and b, the function from the set of natural numbers to itself. The function f is said to be omega if there is a constant c which is greater than 0 and a natural number n0 such that the equation will be this. Mathematical representation of omega notation. Omega g of n equals to f of n. There exist positive constants c and n0 such that g less equals to cg of n less equals to f of n for all n greater equals to n0. Let us consider the same insertion sort example here. The time complexity of insertion sort can be written as omega, but it is not very useful information about insertion sort, as we are generally interested in the worst case and sometimes in the average case. Examples. Here some examples are shown. Please note, here U represents union. We can write it in this manner because omega provides exact or lower bounds. Second one, theta notation. Theta notation encloses the function from above and below. Since it represents the upper and the lower bound of the running time of an algorithm, it is used for analyzing the average case complexity of an algorithm. Theta add the running times for each possible input combinations and take the average in the average case. Again, in the right side, the graph is shown. Let g and f be the function from the set of natural numbers to itself. The function f is said to be theta if there are constants c1, c2 which are greater than 0 and a natural number n0 such that the equation will be this for all n greater equals to n0. The above expression can be described as if f of n is theta of g of n, then the value of f of n is always between c1 g of n and c2 g of n for large values of n, where n is greater equals to n0. The definition of theta also requires that f of n must be non-negative for values of n greater than n0. The execution time serves as the both a lower and upper bound on the algorithm's complexity. It exists as both most and least boundaries for a given input value. Mathematical representation of theta notation. Theta g of n equals to f of n. There exist positive constants c1, c2 and n0 such that the equation will be this for all n greater equals to n of n0. Note please, theta g is a set. Again, Some examples are shown where theta provides exact number bounds. The third one, big O notation. Big O notation represents the upper bound of the running time of an algorithm. Therefore, it gives the worst case complexity of an algorithm. It is most widely used notation for asymptotic analysis. It specifies the upper bound of a function, the maximum time required by an algorithm, or the worst case time complexity. It returns the highest possible output value for a given input. Big O, it is defined as the condition that allows an algorithm to complete statement execution in the longest amount time possible. If f of n describes the running time of an algorithm, f of n is g of n if there exists a positive constant c and n0 such that the equation will be this for all n greater or equals to n0. And the left side, the graph is shown. It returns the highest possible output value, big O, for a given input. The execution time serves as an upper bound of the algorithm's time complexity. Mathematical representation of big O notation. Big O g of n equals to f of n. There exist positive constants c and n0 such that the equation will be this. For example, consider the case of insertion sort. It takes linear time in the best case and quadratic time in the worst case. We can safely say that the time complexity of the insertion sort is big O n square. Note, big O n square also covers linear time. If we use theta notation to represent the time complexity of insertion sort, we have to use two statements for best and worst cases. The worst case time complexity of insertion sort is theta n square. The best case time complexity of insertion sort is theta n. The big O notation is useful when we only have an upper bound on the time complexity of an algorithm. Many times we easily find an upper bound by simply looking at the algorithm. Again, some examples are shown here. U represents union. We can write it in this manner because big O provides exact or upper bounds. Thank you.